12.4.2.1 details the horizontal seismic load effect, EH. The first equation calculates EH as rho times QE, where QE is the effect of the seismic force from V, our base shear, applied simultaneously in two orthogonal directions. Now we'd use a different equation from 12.4.3.1 if we're using the overstrength factor instead of rho here. 12.4.2.2 details the vertical seismic load effect, EV, which is solely based on the dead load and our SDS spectral design acceleration value. Section 12.5 details the orthogonal load combination procedure, which is based on the seismic design category. For the orthogonal load combination procedure, the structure should be analyzed for 100% of the force in one direction plus 30% in an orthogonal direction. The idea is that we choose directions here to create the most critical load effect. So we won't get bogged down too much in the values here, especially if the recommendation is to use the software. But the main idea is they want you to find the most critical load effect, the situation in the most critical load effect is happening, and we'll do our design for that case. So the main equation for base shear in the equivalent lateral force procedure is V equals CS times W. W is the effective seismic weight, which we take as the dead load plus 25% of the live load, the floor live load. In our case, and there are a few more things you should add in if you're analyzing a building. So we're analyzing the entire abutment as a block. So in this case, the dead load will be the combination of the ramp, tower, tiers, anchor, and vertical force from the cables under the walkway weight, and our live load portion is the vertical force from the cables under the live load weight. CS is our seismic base shear coefficient, and this is calculated by the following equations. So here, there are a lot of equations here, but it really just depends on the fundamental period of the structure compared to our TL, which is another mapped value called the long-term transition period. And we don't have these mapped values for our case, but if you run the numbers, you'll see that because our structure is so rigid, it is highly likely that T is less than or equal to TL. And finally, we can get our base shear value, which we can apply in an orthogonal load combination to get our horizontal seismic load, which we then plug into the ASD or LRFD combinations from above. So this is where I'm going to end the seismic load analysis. I'll move up to those combinations again for you maybe. Similar to wind analysis, we have defined the loading, and when we then would now move on to checking our design or designing the main force resisting system for these lateral loads. Moving forward, we would begin to apply this load on our structure in various combinations to elicit the maximum effect. And in a multi-story structure, the force would be distributed based on portion of the seismic weight. In a rigid structure like this, each story is analyzed around its center of rigidity. So like I mentioned before, the abutment is highly irregular and would be best analyzed in a software program for accuracy. We would also need to go forth and check the soil structure interface, which is discussed in Chapter 19 of ASC 7. This would hinge on a more detailed geotechnical report, so we could dive into things like liquefaction potential and the capacity of our soil and foundation to handle the abutment loads during a seismic event.